Hi, everyone. I'm Mike McLeod, editor of Design Engineering Magazine, and thank you for joining us this morning. Today's webinar, How to Accelerate Product Development and Increase Machine Uptime Through Effective Stage Design, will look at the basic steps in developing a stage solution, and it will take a deep dive into how to select product based on application criteria, among other related topics. If you have questions during the presentation, please type them into the GoToWebinar interface, and we'll answer them at the end of the presentation. Also, there are a number of handouts available for download under the Handout tab, including the slide deck that you'll be watching today. With that, I'd like to introduce our two presenters today, Nicole Villacourt, NSK's Automation Marketing Manager, and Jason Wong, Application Engineering Manager for NSK. Take it away, guys.
All right, thank you, Mike, and good morning, everyone. So we're really excited to be with you this morning and share some of the insights and lessons we've learned over NSK's 40-year history designing and manufacturing linear stages. Again, my name is Nicole Villacorta, and I'm the Market Manager for Automation at NSK. And presenting with me is Jason Wong, our Application Engineering Manager for Linear and Mechatronic Systems. So we're here today to discuss how to design a linear ball screw stage effectively, and also show you some options of pre-assembled custom systems to help accelerate your product development and increase your machine uptime. So we'll kick things off by starting with why it's important to design a stage well. We'll look into some of the factors to consider to ensure success, both internally in your organization as well as for your customers. Then we'll provide an overview of linear stage design, do a deep dive on the critical components like your linear guide, ball screw, and support bearings, show some examples of various stages we've developed over the years, and then wrap up with some next steps. So design directly translates to performance, and performance determines your ability to solve problems for your customers, differentiate yourself from competitors, and improve your overall customer experience. So through the tools that we'll introduce today, our goal is to help you design your linear stage in order to optimize your machine performance, achieve reliable output so that's both consistent and accurate, ensure manufacturability of design, develop the best footprint, and help you balance the criteria for performance, quality, time, and cost. So in every project, it's important to consider not just the tactical achievement of the design criteria, but the overall goals of the project. To help you align all of your key stakeholders, first we'll need to define the purpose of the system. Once that's been identified, then we'll look into the design criteria and prioritize based on the budget and timeline. There's always going to be a compromise, whether it's time, money, or other resource, but if all your stakeholders agree on what's most important, then we can align the resources accordingly. Then, of course, there's defining the stage requirements, and we'll dive into more detail in the coming slides. And then finally, there's the option to recruit partners who have the expertise in the critical areas, especially areas that maybe you don't have competency in. So identifying partners that can support critical elements in your design process, offer insight to help you accelerate your design or increase your performance. And depending on the level of complexity and time that you have available, you may decide to either do it from the ground up, use some off-the-shelf pre-assembled actuators, or work with a partner who can help you design the system based on your specifications or build it based on your design. So at this point, I'll hand things over to Jason, who will walk you through the overview of the linear stage as well as the deep dive.
All right. Thank you, Nicole. I'm really excited to be here today. I've been doing linear stages for a very long time, and it's just something I'm really enthusiastic and just really love to do. It's super interesting. Next slide, please. So when we look at a linear stage slash ball screw stage, we we usually want to understand the design criteria of the stage. So all the criteria on the left-hand side of the screen in red, how is the stage oriented? What's the payload? What kind of forces are on it? So all these things that engineers are really keyed into, like how fast are you moving? How accurately does it need to be? Does it need to position? How big can it be, or how small does it have to be? Or using it outside in a dirty environment or in a clean room or someplace where it's really nasty, and then motors and drivers. So the things that help us to get the stage to move. So those are the things that we're interested in defining when we first look at a stage. And then all those specific criteria go into developing the so-called design elements. So that's the gray in the middle. Sizing your linear guide and ball screw, defining the specs for those components, how accurate it needs to be. Does it need to be preloaded or not preloaded? And then the overall envelope of the mechanism. And then for our products, the linear products, we need to decide what kind of grease do we use in it based on the environment, and any kinds of special materials or corrosion coatings we need to combat the environment that we're using the stage in. And then, of course, the motor sizing selection. So these are the basic elements that we look for when we look at designing a stage. And without these elements, it's very difficult to home in on the optimized design. But this is truly the basis for what the design is based on. Next slide. So when we look at a stage, I'm specifically talking about the stage described in the right-hand image. And this is a super basic stage, basically consists of base plate, 2 rails, linear guides, a ball screw, a carriage, ball screw support bearings, motors, motor brackets, those types of things. So this is the most basic stage that I'm talking about. That's what we're going to go over today. So the items in red toward your left, those are the items that specifically are required for a stage. Of course, we need a base plate, linear guide, ball screws, motors. And then the items in black, those are the optional items. Hard stops, a limit sensor and length flag, and possibly a linear scale depending on the accuracy of your stage. So this is the basis for what we're going to talk about today. Of course, you can go way off into the extreme and develop something really complex, but today we're just going to talk about this for simplicity. Because this presentation is intended to teach you how to make a stage. It's just to give you the methodology in which we look at how we design the stages and what things are critical to us. Next slide. So this is kind of a slide that kind of describes where we could, depending on your capability or your desire, we could substitute pre-assembled stages such as like what we call an MCE actuator, which is a pre-assembled actuator with motor, or in some instances we could try to substitute a ball screw for a ball screw motor assembly if we wanted to try to simplify it in different ways. But this is just a slide to kind of give you a flavor for where you can substitute different products based on what you need. But we're really going to deep dive into the traditional make from scratch actuator. Next. So we're going to look at the components. Today we're going to talk about the linear guide, ball screw, support bearings, and other considerations about designing a stage. First will be linear guides. So traditionally, for clarity, we consider a linear guide as shown in the image on the right, traditionally a rail and a slider, and traditionally rolling elements being balls. So what a linear guide is intended to do is provide free motion in one direction, basically the direction of your slide, while supporting the forces and moments in the other directions. So that's what the linear guides are traditionally intended to do, and that's what their purpose is in our linear stage. As far as the requirements for a linear guide those are the items 1 through 8. We look at these types of elements when defining the linear guide. Of course, the size and series, how long is it, how many sliders or blocks do we have on the rail, how many blocks are on the rail, what's the material, the coatings, accuracy grade, whether it's preloaded or clearance, and then also the lubrication. So these are the elements that we look for in defining the specific product in which we use on the stage. Next. So the basic flow chart that you see here is how we go about selecting the linear guide. And it's based on the expected life of the stage that we want to achieve, and also the environmental conditions that the stage is going to see. So traditionally, our first step is once we get the specifications, to look at the free body diagram of the stage that we're going to design, and then come up and define the loads that are being applied to this stage, and then translate those loads into the loads at the linear guide itself. Step 2 is once we understand that free body diagram, we decide what's the resultant load or the mean load at each block. So that helps us to understand what load we're going to use on our life calculation. So that's step 3. Once we know what the load is at each of our sliders, we can do one of two things. We either can calculate what the life is going to be based on a particular linear guide, or we can so-called back calculate the load rating of the linear guide that we need based on the expected life that we want to achieve. So that's step 3. Step 4, as a double check, we want to make sure that our selected linear guide can handle any large static loads that may be applied. So this is a contact pressure check for us engineers. That's we're looking to make sure that we're not so-called going to dent the balls in the linear guide, which will decrease the life of the product. And then finally, step 5 is once we've selected the basic linear guide, we go back and say, okay, do we need any special materials or coatings applied to that particular product to accommodate the environmental conditions in which the stage is being used in. So those are all the elements you see in the bottom of the slide regarding environmental or usage condition type criteria that we want to optimize our linear guide for. So again, the materials, the coatings, the accuracy grade, those types of things. Lubrication is very important for our product. Next. So for us engineers, this is a screenshot from our catalog. It is basically the free body diagram and analysis techniques we use to come up with those loads to help us decide what's the life of the linear guide going to be. So I'm not going to go into this too much, but this is in fact the technical detail that you would use to come up with those loads. Next. So once we come up with the load, this is just the basic calculation I wanted to show you. There's a calculation for the life, which is L. And then in the equation, you'll see a C50, which is actually the load rating of the linear guide, and then a FM, that's the actual load that the linear guide sees. So it's a very basic equation, essentially load rating of the linear guide divided by the load, cubed times 50, and that is the life of the linear guide. And traditionally, we calculate this in kilometers of running life, so we can know how long the stage is going to last as far as distance, and then we equate that distance to commonly what's the stage travel / stroke. Usually it's cyclical, like back and forth, 100 millimeters, and then we can calculate how many cycles that is, and extrapolate that to how many years this particular stage can work under that load condition. Other things that we look at as far as the linear guide life, we make these basic assumptions. The linear guide life the linear guide is properly maintained with adequate lubrication for the life of the product. and the linear guide is properly mounted with minimal misalignment. So these are assumptions that go into this calculation, assumes these particular things, and you can imagine if you forget to lubricate your linear guide, it's not going to last very long. If you expect it to last 10 years, there's no way a linear product is going to last 10 years if you don't add grease to it, essentially. And if you misalign it during the installation, you're basically adding loads that the equation cannot compensate for. So then you get a decreased life of what you're not expecting. Other things like FW as a load factor takes into consideration environmental conditions. So those are the basic equation for life. And like I said, we traditionally calculate linear guide life in travel distance, so kilometers of motion. Next. So it's the next component we're going to talk about is the ball screw. And ball screws, as you can see on the right, basically a shaft, a threaded shaft, and a threaded nut that goes along with it. And again, it has the basic specs that we're going to look for: shaft diameter and lead, which dictates speed or thrust, those types of things. And then we also look at the design of the ball nut based on what the load capacity and speed rating are, and rigidity, depending on the specification of the stage. And then we're also interested in inherently how long is it, and what's the geometry on the end journals of the ball screw shaft to accept your support bearings, which handle the axial load of your ball screw shaft. And then again, the materials and the coatings, accuracy grade, preload, and lubrication. So those are the specs that we look for in developing and defining the ball screw specs exactly. Next. So based on a similar diagram, which you just saw for linear guide, we go through the same process for the ball screw. We come up with the resultant load that the ball screw is going to see in the axial direction. We start looking at what's the diameter and lead for that particular ball screw, and we then, using that load rating for that particular selection, we calculate the expected life of the ball screw in step 3. And then commonly we'll look at that life in comparison to the linear guide life versus the stage life and decide, okay, where is our current weakest link in the design? Do we need to upsize our ball screw to increase its life, or is that life sufficient? Or is the linear guide life now, too low? So we kind of do an iterative game on how we adjust our ball screw. Do we need a little bit larger ball screw? Do we need to increase the length of the ball nut? Okay. Do we need to increase the length of the ball nut? Those types of things to essentially iteratively upsize or downsize, or is the linear guide okay? Or the ball screw, is it okay? And once that's done, we go back and just double check for the ball screw that we picked at step 4. Is the contact pressure okay? Make sure that no static load applied to the ball screw is, again, going to dent the balls in the ball screw and eventually degrade the life lower than we expected. And then step 5, again, look at the basically the materials used to combat the environmental conditions. Materials, coatings, accuracy grade, preload, greases. Again, the same thing that we just did for the ball screw. Now we just did. Next. This is the ball screw life calculation. Again, it's very simple. It's a cubic calculation, as we talked before with the linear guide. So basically a load rating divided by the load that the ball screw sees. There's a couple of ways in which the calculation can be done or derived. There's commonly an equation for life in revolutions or life in hours, or the calculation that I like to run, which is calculating the life of the ball screw in running distance, which takes into account the lead of the ball screw. So it's easy to equate the life of the ball screw to the life of the stage. in addition to the life of the linear guide, also in running distance. Some of the assumptions again for this life calculation, again, proper lubrication of the ball screw, proper alignment, and then a third one for ball screw is that the ball screw receives only axial loads. So, and what that really is intended to say is that if you misalign the ball nut, you're basically again applying loads to the ball nut that weren't expected. So your life is going to be degraded, and then people find out that, oh, why is my stage dying early? Well, because the stage was misaligned from the beginning, and the ball screw died short life. Again, we also have load factors, FW, to compensate for load conditions or operating conditions. Commonly, like I said, it's 1.2 to 1.5, basically safety factors that we add into the life equation to give you a better understanding of what's the theoretical running life. Next slide. Ball screw support bearings. So what these are, we need something to support the axial loads of the ball screw. So commonly we need a support bearing, and the traditional support bearings are angular contact bearings, as you see on the right-hand image, and in DF combination or face-to-face. And depending on the life requirements, we can go to different combinations, like a 3-bearing set, that's the middle image, or maybe a 4-bearing set, that's the very far right-hand image. So that's what we do when we look at bearing combinations. But the selection of that is based on, again, the life calculation for the support bearing. It's the same calculation that we just did for the ball screw, other than that we substitute the load rating of the support bearing in place of the ball screw, and then use the same axial load that we had for the ball screw to calculate the life. So it's the same basic calculation, just that we substitute the load rating for the bearing in place of the ball screw. And traditionally, for support bearing sizing, we of course start with essentially one size smaller than the ball screw that we've selected in terms of diameter. So if we started off with a 20 diameter ball screw, we'd start out with a 15 diameter bearing. And then if we had to, we'd go from either a 2-bearing set to a 3-bearing set or a 4-bearing set based on what the support bearing life looks like. And then we double check at the end after we pick our support bearing, make sure we don't exceed the maximum load of that support bearing. Again, that's they call it the load limit. And essentially we're verifying that the contact pressure is not too high to possibly dent the balls in the bearing itself. Next. Okay, so our support bearings come commonly housed, and that just means that instead of having to make your own housing, you buy a support bearing that's pre-housed in a machine metal housing, different shapes for us, either square or round, and usually based on how we want to implement the bearing in the design of the stage. So in that original stage that you saw, we probably used a square type, since the square type was easy to mount to our base plate. But depending on your stage, you may like a round type. As far as how we, what the arrangement of the support bearings are, the most common way is what's depicted in that lower picture, this fixed simple arrangement. So the fixed pair being an angular contact bearing set on one end of the ball screw, and then a simple end bearing on the far end of the ball screw, they call it. So that's a radial bearing on that far end. This is the most traditional way in which a ball screw is supported by its bearings. A couple other things about our support units: pre-grease, so you don't want to be out there and forgetting to put grease in your bearings. So we sell pre-grease support unit bearings, and then Ours, some support unit bearings, at least ours, come with anti-corrosion coating, so you're not having to deal with any kind of corrosion issues for your bearings. Next. Okay, so we've basically finished the component design as far as the linear bearing ball screw for the. So we're going to move into the design of the base plate and carriage of the stage. One of the most important aspects of that is proper alignment of our linear components, our linear guide and ball screws in the stage. So I'm gonna talk to you about this concept of 3 reference edge concept, rail slider. And that has to do with the upper right-hand picture. And really what we're trying to show you here is how we design the base plate and carriage to achieve proper alignment of the linear guide and ball screw. So traditionally, when we make the base plate, we rely on machining in parallel grooves into the base plate so that when we install our linear guides, we get parallel rails. And then we also, and in that manner, instead of having to manually make the linear guides parallel, we've machined in the parallelism into the base plate. So based on our CNC machines of today, we can get nice, smooth base plates, perfectly machined with perfectly parallel reference edges. And then when we install linear guides, the linear guides are perfectly parallel. So traditionally, this concept of this rail slider concept, we do 2 reference edges for the rail. They call it the reference side and the adjusting side, and then 1 reference edge on the carriage. So, and we leave one side, the adjusting slide, floating per se, between the top of the slider and the carriage itself. So that provides us with the best conditions for properly aligning the linear guides and keeping them parallel with zero binding of the carriage as it moves from one end of the stroke to the opposite end of the stroke. There's also some other considerations, which is the bottom right-hand table. And this talks about, again, the parallelism of the grooves that were just machined in your base, but also talks about the planarity of those 2 surfaces in which your linear guides sit. So we like to keep not only parallel linear guides, but we like to keep them on the same plane. So what you'll see is a table on the right-hand side that talks about the minimum specifications for these parallelism and planarity that we'd like to see for each type of linear guide. And your stage, in fact, may be more tight, so we may need to hold those specifications tighter just to meet your stage requirement. Next. I think this is the last slide about designing your stage. Traditionally, we have baseline requirements that we use based on industries for our linear guide and ball screw product. So there's some different examples of how we go about selecting our materials and greases and coatings based on specific industries or applications. So just a couple I'll mention, like general industry. Okay, we're just going to use standard carbon steel product with standard grease. That's the most basic. You may go into a wash down or splashy environment. So we may want to look at stainless steel products with some kind of corrosion coating. Let's see what else we have here. Food or medical. Again, we expect people to be wiping down their equipment, so we may want stainless steel product with maintenance-free seals, food grade type of product, and then food grade greases. So these are the types of things that we consider and have already defined based on the industry what types of materials and coatings and greases we'd like to use. So this is just give you a kind of a broad flavor how we do things at NSK as far as material selection. Next. Okay, that finishes up the basic of the stage design for what we have today. It's very brief, but it's a good thumbnail about how we go about it, kind of the methodology and style. I got some different slides here that I'm going to show you of different stages that can be made. So now we went from super simple. These next 4 slides you're going to see are some stages that are like, whoa, way out there. So this is a large stage. It's actually a 7-axis stage, and all these stages that you're going to see were designed by our NSK Japan facility, not designed by me specifically, but just some things to go over, just kind of give you a flavor for what's going on here. This particular stage is canted at 70 degrees. I don't know why, but essentially it's vertically oriented, and so you get some large travel distances, 2.5 meters, 2 to 2.5 meters in strokes. And huge payloads. Speeds not too bad, 600 millimeters per second type stuff. So this is just a stage, just gives you a flavor of what can be done once you start developing and designing your own stages for your own equipment. Next. It's another stage that was developed. It's an X, Y, theta table. So that means there's 2 linear axes and a rotational axis. You can see some of the specs that I've outlined. Payload 5 tons, so that's 10,000 pounds. So they got some different step sizes for the motion. So there's a rotary motion, and there's also a linear motion, 0.03 microns per step in the X and Y. So very high resolution motion as far as this particular stage. And then repeatability down in the minutes and or microns, depending on which axes you're looking at. Next. This stage looks like it was designed for clean rooms. It says a downflow fan. A little bit different geometry than what we've seen before. Got different kinds of coating, electroless nickel coating. What else they got? Stroke, 1 meter square type stroke. Positioning repeatability, plus minus 1 micron. So very highly accurate stages and relatively, not too large, but pretty large, with some special finishes, probably for the environment. Next. All right, this is the last one. This one says it's an all stainless steel XY theta table. So that means 2 axes of linear and 1 rotational. Looks like they had to use some special materials, stainless for corrosion. 20 kilogram payload, about a meter square stroke with plus 3.5 degrees of motion. So they have a little bit of rotational capability here. Repeatability 4 plus minus 4 minutes, 1 micron. So another very high-end stage, but based basically on the same products that or the same concept that I showed you originally, just specific for this particular application. Next step. So I'm going to pass this back to Nicole. She's got a few slides left, and we'll finish up the presentation / webinar for you today.
All right, thank you, Jason.
Nicole. Yep.
So now that you have the tools to design a linear stage, there are several options available for you depending on the level of complexity that you want to tackle, as well as the time you have available for both the design and the manufacturing or assembly. So the first option is to design your stage from scratch. So that entails doing all of the steps that Jason mentioned earlier, so designing all your components. One good thing about this is there are many options available out there. We showed you some examples of the NSK ball screw, linear guide, support bearings, as well as accessories that you can incorporate, like combination brackets for your XYZ assembly, motor mount brackets, sensors, or covers. The second option is using an off-the-shelf actuator system. So these are pre-configured and pre-assembled actuators. And the nice thing about this is it's much easier to integrate into your design, and it's also simpler to maintain. So one example is the electrified monocarrier, which you see here on the right, that has a Sanya-Denki a stepper or servo motor. Another option is the motorized ball screw actuator, which Jason showed in the earlier slide, that has a ball screw directly coupled to a NEMA 17 motor. Then the third option is finding a partner to design this with you. So this means doing a custom design system. And the great thing about this is it's fully optimized to help you maximize your performance, your space requirements, as well as life. And one option that we have here at NSK is our integrated mechatronic systems, or what we call our XY series internally. So these are fully custom systems that is designed for your application. So for more information, you can visit us at our website, nskautomation.com. Feel free to download the resources available on this webinar. At this point, I'll hand it back to Chris for Q&A.
Thanks, Nicole. So we have another poll to take and a few questions to go over. First off, Nicole, could you talk a little bit more about the pre-assembled? Now, most of the presentation has been about doing it from scratch, but you mentioned there at the end about pre-assembled or custom built. Could you talk a little bit more about that?
Sure. So our goal for our customers here is to help them simplify as well as optimize. So the pre-assembled actuators were designed specifically by our mechatronic engineers so that we can help our customers make it easy for them to design in these stages. So this entails, for example, our MCE, which is shown here on the upper left corner of the integrated mechatronic solution. So those first two pictures there. So these are highly compact and a cost-effective alternative to building your linear stage from scratch. As you can see, it comes mounted with a Sanya-Denki stepper servo motor, which you can do either inline or parallel. And it also comes standard with our long-term maintenance-free K1 lubrication units. So these are available in our quick ship program. That's 4 to 6 weeks of delivery for the most popular sizes, and includes all the options for accessories as well as our double slider stage, and any other configurations that the customer would want. So that's the first option. The second option is our motorized ball screw actuator, which is shown also in that gray box. So that's the lower left corner. And these are compact linear motion systems with high accuracy and repeatability as well as reliability. So these MBSAs are precision ground ball screw that's directly integrated into a NEMA 17 stepper motor. It has a space-saving design because you eliminate the motor coupling that usually comes in between, and it achieves a longer life since it uses a precision ground ball screw, which compared to a lead screw is much more efficient, smooth, and has zero backlash. So all of that just adds to extending the life of your equipment.
Got it. Okay. And building off that, Jason, so companies that, customers that had a specific application, they could come to NSK and just sort of give you their specs or their needs, and you guys could build like a custom table or a custom guide
System.
Yeah, system.
Yeah, as far as NSK looking at and reviewing specific customer stage requests, yeah, of course we're welcoming people to do that. We of course want to look at again the specifications, like I had defined way up front in the presentation, to help us understand what the customer physically wants, what's the how large is it? Does he need, multi-axis, single axis? Is he looking to use a specific motor? What's his payload? So all those things go into NSK considering making a stage. Just being engineers, we like to dive into all these little details, these nooks and crannies of the design before we answer. But certainly, we're willing to look at any stage that's required. And just based on our history of making stages, we have plenty of capability to design stages. We just like to be thorough in our methodology and how we design the stages because we want our customers to be perfectly satisfied. We feel good about the design that we put out to them. So.
And the all stainless steel XY theta table, how do you guys achieve the specs on something like that?
Let me just look at it real quick. On that particular stage, I think what's most difficult about it are going to be the repeatability specifications. So repeatability of motion is commonly described as moving to the same position in the same direction. So if you're, which we call unilateral positioning repeatability. So that means that we've essentially taken out the backlash of the ball screw and or motor as we're always moving to the same location in the same direction. So based on these specifications for the linear positioning, we're probably using a high resolution encoder on our motor, which gives us the repeatability or the step size that we want to achieve the repeatability spec. And as far as the repeatability of the rotational axis, this particular system probably was designed with it does actually say a direct drive axis. That means a motor that directly drives the theta axis. So that design is probably one of our Megatorque mirror motor series products, and that has a high resolution resolver as the rotational sensor. So right now, for our current design of resolvers, they resolve down to like 2.6 million, they call them steps per 360 degrees. So that's what we can resolve that one turn of motion into is 2.6 million steps. So that's how we're achieving that positioning repeatability on that all stainless steel XY theta table.
Great. Okay. Well, that is all the questions that we have for today, and I'd like to thank all of our attendees for coming today. If you think of a question later that you'd like answered, Nicole and Jason's contact information, if we can get that last slide, should be on the screen. Also, a recording, an on-demand recording of this presentation will be made available and will be sent out to everyone who attended today, and will also appear a link to the registration, and the on-demand video will be available on the Design Engineering website. And with that, thank you and have a great day.